Hey guys, and welcome back to another video on the channel. In today's video we're going to be doing part 2 to the Specialist External Exam Short Response Paper 1 for 2020. So in the last video we just finished up this question here with the vectors, and now I'll be continuing on to question 16, which is a proof by induction. Oh my gosh, that looks very fun. Let's see how you do it. So with proof by induction, you start by proving pretty much the most basic sentence. Does it work for n equals 1? So given cos theta cannot be 0 and n belongs to every positive integer, so that's pretty much what that statement there says. Use mathematical induction to prove that this side, this monstrosity that goes on for infinite, is equal to this thing here. So not going to lie, this is a very intimidating question straight up, but let's try and break this down and see how you would actually answer it. Now, this would be very hard to answer in exam conditions because it's just a monster, but straight off, let's just use our proof by induction. So you start with, alright, is it true when n equals 1? So all you got to do is go n equals 1. So all you do is you ignore this infinite thing here and you just look at this statement here. The front statement where you have this bit here and sub in n equals 1. So the left hand side and my right hand side. So substitute n equals 1. You're going to have negative 1, 1 plus 1, cos of 2 times 1 minus 1 multiplied by theta is equal to 1 minus negative 1 to the power of 1 cos of 2 times 1 times theta all over 2 cos theta. So since I have limited room here, well, I still have a lot of room, but I might rub stuff out just to fit all of this in, but I'll make that decision when I get to it. So here we've got negative 1 to the power 2, which is just 1, so we have cos, and then we have 2 times 1 minus 1, so all we have here is cos theta. Okay. Over here we have negative 1 to the power of 1, which is still negative 1, but it's being multiplied by negative, so you have 1 plus cos of 2 theta on 2 cos theta. Now pretty much what we've got to prove is that this side is equal to this side, so we go straight to our trig identity sheet. So what we're looking for is pretty much to simplify the top half there. So I'd go to my formula sheet here, and I would scroll down and go to this section here where I'm looking for cos of 2a. So we've got a couple things there. We've got that guy there, which we are probably not going to use because we don't have any sine squares or anything like that. But what I am looking for is probably this guy here. So let's just write that down really quick. So cos of 2a is equal to 2 cos squared of a minus 1. If I rearrange this, I have cos of 2a plus 1 is equal to 2 cos squared of a. Is that not our thingy we have up there? So I have cos theta is equal to 1 plus cos 2 theta. If I replace this bit here with that identity, I'm going to have 2 cos squared theta on 2 cos theta. Now recall cos squared theta just means cos theta times cos theta. So hence we have cancel one of those, cancel one of those, cancel that, cancel that. We have cos theta is equal to cos theta. So we've proved it for n equals 1. Now that was quite a handful on its own, just the first statement, okay? So it is true for n equals 1. Now all I'm going to do is just start rubbing stuff out just so I have enough room for the rest of it, because it's quite hefty and it took me a bit to get through it. So let's rub that out. So we know it's true for n equals 1. So the next thing to do in proof by induction is you assume it's true and you're going to let n equal k. Now k needs to be the condition satisfied in the original formula. So what I mean by that is we need to work out what set n belongs to. So in the question here, they've defined n to be a positive integer because of this notation here. So z basically means integers. And they've specified positive, and this symbol here means belongs. So hence this sentence they have up here, n belongs to the positive integers, pretty much. So when you say, alright, assume true, let n equal k, and you need to define k as a positive integer in this case here, where k belongs to z plus, and you'll get your mark there with that bit. Now all you got to do is kind of an easy part, just substitute wherever n is, replace that with k. So we have, I don't know how I'm going to fit this in. Alright, I'm going to write the left hand side. So left hand side, right hand side, we'll just remove that. Left hand side, I'm going to go cos theta minus cos 3 theta plus cos 5 theta plus dot dot dot. Now these dot dot dots mean an infinite amount, plus -1, and replace the n with the k, plus 1 cos of 2k minus 1 theta, brackets. Alright, that's my left hand side. My right hand side, I'm going to write real quick, is 1 minus -1 to the power of k cos of 2k theta all over 2 cos theta. Right. Once you've got that, that's all you've got to do. Now you've got to assume it's true for k plus 1. So what we're doing in proof by induction is proving it's true for n equals 1, letting that be true now for any integer you plug in, which is k, and then we're going to try and make a statement for the integer after the integer k, so hence k plus 1. So all we got to do is rewrite this whole thing except k plus 1. So rewrite this whole line here, but replace that with k plus 1 pretty much. So you're going to have alright, let's scroll down a bit. Okay, so my left hand side, I'm going to have cos theta, I don't know if I'll fit this, minus cos 3 theta. If you guys are wondering, I'm just looking off my sheet because I actually did the exam myself before making the video. That way I wouldn't have to constantly scroll back up to the question. And then I marked it myself, so there were bits I got wrong, but now I've got the correct thing pretty much in front of me. 5 theta, we can leave it like that, minus dot 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 plus -1, and now you replace this with k plus 1. Oh no, not this bit here, you leave this as this first statement, because if you want to do k plus 1, you need to add in the next term, which is k plus 1. So you write this whole thing pretty much, plus 1 cos of 2k minus 1 theta. Then you go plus and the k plus 1 term. So I'm going to write -1 k plus 1 plus 1 cos of 2 multiplied by k plus 1 minus 1 theta. That is not going to fit there. I'm going to rewrite that bit here. Sorry guys. -1 k plus 1 plus 1 cos brackets. The 2 is being multiplied by the entire k plus 1, not just the k, so don't forget to include that in the brackets. So we go 2 multiplied by k plus 1 brackets minus 1 theta. So I'm just rewriting that bit there because it don't fit pretty much. Okay, that is my left hand side done. So now that you've got that pretty much all written there, and you make sure you can simplify it if you want, but leave it for now, we're going to write the right hand side. So I'll go down to the next page, right hand side, and you're going to have 1 minus -1. Instead of k, you're going to have k plus 1 cos of 2 times by k plus 1 theta divided by 2 cos theta. Okay, so as we can see here, this bit here is exactly the same as this bit here, and that bit is equal to this bit here. So we can replace this infinite sum plus, well, we'll leave this bit here because that's not equivalent. So all we're doing is replacing this entire bit in the circle with this right hand side, because this is equal to that. So we'll go and rewrite it down here. So we'll go, my left hand side again is going to be this bit expression here. So 1 minus negative 1k cos of 2k theta divided by 2 cos theta. So that's that infinite expression, and then you've got to add a plus because we've still got this term here which wasn't in the substitution. Negative 1 k. Now I can simplify this. This is in multiplication, so this will be k plus 2 cos of, and we'll simplify this, so we'll have 2k plus 2 minus 1, so we'll have 2k plus 1. Okay, hopefully you can see where I got that from, just simplifying this inside bit. So you'll have 2k plus 1 multiplied by theta, and that's my left hand side. And this is still equal to this right hand side, so I won't write the right hand side again because that'll be the same. So I'll draw an arrow just indicating what it is. So this is still my right hand side, so imagine if I wrote that there, is equal to that. So what we've got to do is try and make all of this pretty much look like that, and that's a struggle. So what we got to do is pretty much combine these two things here. So we can only combine things as fractions when they have a common denominator. So we need to put this whole expression here over pretty much 2 cos theta. So what you're going to do is write this bit here. So go 1 minus negative 1k cos of 2k theta all over 2 cos theta. Now you can add this bit with that if they have the same denominator. So what we're going to do is literally put it over a fraction. So 2 cos theta, and write this whole bit here. Negative 1k plus 2 and cos of 2k plus 1 theta. Now, normally this would be wrong, but if I multiply the top as well by the bottom, I've technically times it by 1. So I've got to put a 2 cos theta there. So technically this has just been multiplied by 1 because that would cancel with that still. Okay? So hopefully you can see what I've done there. But the reason I've done this is so I can add this and this together because they're on a common denominator now. Oh, we're going to run out of room. Okay, so, and it's still equal to the right hand side. So just, I'm not going to write the right hand side. We're just going to try and make it look like the right hand side. So what we're going to do is remove that and put it over one thing. So we'll have 1 minus negative 1 to the k cos of 2k theta plus negative 1k plus 2 cos of 2k plus 1 theta 2 cos theta, and this is all over 2 cos theta. Now, to go any further than this, we need another trig identity. So, if you recall in our formula sheet, we've got a couple identities here, but the one we want to look at is pretty much this bit here, because we have a cos of an angle times another cos of an angle. So what we want to do is go straight to our product identities and take a look at this one here. Let's try and rewrite this bit in terms of that identity. So the identity is cos of A is half of cos of A minus B. So I'm going to rewrite that identity here. So let's write it here. I'll try and make it as small as I can because I don't have enough room. So cos of A and cos of B is equal to a half of cos of A minus B plus cos of A plus B. Okay? So, what we have here is 2 cos of theta and cos of 2k plus 1 times theta. So, because there's a 2 here, we don't need to write the half at the front. So we can rewrite this as cos of, in a sense, 2k plus 1 minus 1 times theta. Okay, that's that first bit there. Plus cos of 2k plus 1 times theta. So, simplifying this, we can write this as cos of 2k theta plus cos of 2k plus 2 times by theta. Okay? So, I can replace pretty much, where's a highlighter? I think this will be a good highlighter. So I can replace this bit here. And the reason I want to do that is because it starts to break things up nicely, and you can see some stuff will actually start to cancel. So what I'm going to do now is, oh gosh, I might go up here and start writing it out again. So we're happy with all this stuff here. If you want to keep a look at this working, just rewind the video, honestly. But I've run out of room, so I'm going back up here to continue writing. It's a shame I can't do it on the OneNote. Anyway, let's rub this out here, and just continue our working. So, hopefully you understood all this stuff here. If not, go back and watch it again. But if you do have any other questions about this induction, because it is quite a hard induction question, leave some in the comments and I'll try my best to answer it. Or I might do this in a separate video with more writing room and being able to use my highlighters a bit more. Okay. But this is definitely an A-level specialist question. Not a lot of people would have got this right because there's a lot of stuff you need to be using. Okay, so what I'm going to do is rewrite this whole line. I'll show you which line I'm going to write. I'm going to rewrite this whole line up there. So I'll have to go back and refer to it. So write it as, I'll write in a different color so you see this is new working. 1 minus negative 1k cos of 2k theta plus negative 1k plus 2 cos of 2k plus 1 theta 2 cos theta divided by 2 cos theta. So that is just what I've written here, and now I'm going to replace this bit here with that bit there. So I'll write it up here. So this bit, is that a highlighter? No, it's not. So thing I'm going to replace is just this bit here with this following expression that we just worked out, cos of 2k theta plus cos of 2k plus 2 times by theta. Okay, so I can rewrite this whole thing as 1 minus negative 1k cos of 2k theta plus negative 1k plus 2, and it's being multiplied by this replacement here. So this bit is going to be that bit now. So we'll have cos of 2k theta plus cos of 2k plus 2 brackets theta brackets all over 2 cos theta. Okay. Wow, that was a lot. Holy dooly. Okay. So what we can do now is pretty much start taking a look at this specific terms here. So negative 1 to the k can be 1 or negative 1, depending whether k is even or odd. If k is even, it will be 1. If k is odd, it will be negative 1. But let's take a look at the other expression as well. Negative 1 to the k plus 2. It will be 1 or negative 1, depending if k is even or not. Now, it doesn't matter what k is. If k is 5, this will be negative 1. So negative 1 to the power of 5 is the same as negative 1 to the 5 plus 2, because both of these will be odd. So they'll both give the same result. So hence we can actually equate these two in this expression here, which is the hardest part of this trig proof. I actually got stuck on this bit and I had to go look at the answer, but now it makes sense. But holy dooly, that is quite a leap you need to make in this exam. So, using that fact, we can actually equate these two things here because they're both going to give the same answer regardless of what k you pick, purely because of this fact here. So, what we do is, alright, let's multiply this guy here and here. And we're gonna basically make these two equal to each other for now. So I'll write that in the corner up here so I don't forget it, and I can use more writing room. So -1 to the power of k is equal to -1 k plus 2. That is equivalent, regardless of what k is, these will give the same answer, 1 or -1. So, distributing this bit here, what we get is pretty much -1 minus -1 k cos of 2k theta plus -1 to the k cos of 2k theta. Now I'm only going to change this first term, only this one here. I'm still going to leave this bit with -1 to the k plus 2, and you'll see why in a sec. Plus -1 k plus 2 cos of, oh, that's not going to fit, 2k plus 2 theta. That's terrible writing. Anyway, okay, so the cool thing we can do now is that, let's rub that out again. So the cool thing we can do now is you can see this is just the negative of this term here. So hence they actually just cancel out, so we can just use a black pen and just cross those guys out. So what we're left with is, alright, we're going to leave this bit here, but we're going to start rubbing this stuff out. Okay, so rub that out. Just so we have enough room. Alright, so I'm going to rewrite this bit here. We have -1 plus -1 to the power of k plus 2 cos of 2k plus 2 theta on 2 cos theta. And you can see they're almost the same. There's just one little thing we've got to do. -1 to the power of k plus 2, using our index laws, is the same as -1 times by -1 to the k plus 1. So hence, this term here turns into a negative term. And this can be reduced to a power of 1. So, we can see they're equivalent. All we got to do is actually just factor out a 2 here as well. And your left-hand side, this entire thing here is now equal to this entire thing. Wow, that was a lot. We're 23 minutes in, and that's just question 16. I can't imagine doing this in exam conditions. I would have got stuck at this bit here. Like, I got the trig substitution, but the -1 to the power of k was the really hard part about that. Okay. But anyway, let's move on to the next question. Alright. Now, I know what you're thinking, that one looks very hard, but this one's actually significantly easier than the proof by induction. I actually think this should be worth like 8 marks, honestly, or 10 even, because that's ridiculous. Okay, let's get on to this one, but somehow this one's worth more. Don't get me wrong, this one's quite hard, but it's a lot easier than the proof by induction. So, all we got to do is determine the smallest value of a given the integral from -a to a. All this monstrosity is equal to 1. So what we're going to do is we're not even going to bother integrating yet. We're just going to look at the trigonometry. So sec of, oh, that's terrible writing. Yeah, let me know what color you guys like me writing in. So I'm going to use black from now on. Sec plus tan of 2x on cosec 2x plus 1. Okay. let's just start simplifying this. So we can rewrite this because sec is 1 over cos, so we can write that as 1 over cos of 2x plus, and tan is the same as sine on cos, so that would be the same as sine of 2x on cos of 2x divided by, now cosec, we'll leave that for now as just this, but you can see the top part of my fraction here I can actually combine because they have common denominators. So I'll rewrite this bit, but yeah, you can see this can combine with that, so what we get is pretty much 1 plus sine on 2x all over cos of 2x all divided by cosec of 2x plus 1. Okay, so hopefully you can see all I did was combine these two because they have common denominators of cos of 2x. Okay, now what we can do now is take a look at cosec. So recall cosec of an angle is 1 on sine of that angle. So let's replace that bottom bit with a sine, pretty much. So what we're going to do is pretty much write our top half. So we'll have 1 plus sine on 2x on cos of 2x on 1 on sine of 2x plus 1. Now I want to combine pretty much, let's use blue. I want to combine this with that somehow. And the way you can do that is make them have a common denominator. So you can rewrite 1 as sine of 2x on sine of 2x. Okay? So if we do that little stuff there, this is what we get. So 1 on sine of 2x plus sine of 2x on sine of 2x. And now I can add them together because, as you can see, those have common denominators. So what we get is 1 plus sine on 2x on cos of 2x all over 1 plus sine of 2x all over sine of 2x. Now, hopefully you can see that is the same as that. So let's rewrite what we actually have here. We have 1 plus sine of 2x on cos of 2x divided by all this, which can be written as times sine of 2x on 1 plus sine of 2x. So all I did was rewrote this in terms of its normal stuff here. And you can see, since these guys are the same, you can actually cross cancel because they're being multiplied. So what we can do is just chuck a big red dash through both of them, and that whole monstrosity, let's go back to black, turns into sine of 2x on cos of 2x, which is tan of 2x. So that whole trigonometric mess just simplifies to tan of 2x, pretty much. Righto, so now I'm going to write the integral out now. So the integral from negative a to a of 1 plus tan squared of 2x dx equals 1. So all I did was replace that with tan of 2x, sorry, and you get 1 plus tan squared. Now we can't integrate this just yet, because in the specialist formula sheet, if we go to our differentiation stuff, we don't know how to integrate tan squared, but we do get given a lovely trig identity as well. So it always comes back to trig identities in this specialist external. Take a look at that one there. Does that or does that not look exactly what we have in our question here? So what you're going to do is just chuck a big bit of highlight on that, and you can replace that. Let's just write it down here because I'm lazy. The integral from negative a of a sec squared 2x dx equals 1. Now the reason I did that is because if you go to the specialist formula sheet, you are told that specific integral. That is equal to tan x, because the derivative of tan x is sec squared x. So when you integrate this, you're going to get, well, you've got to do chain rule. So you've got to divide by the derivative, which is half tan of 2x from negative a to a is equal to 1. Okay, so all I did was a u sub on that, which is probably the easiest part of this. Now you substitute a, so you get a half tan of 2a minus a half tan of negative 2a is equal to 1. Okay, so what we do now is pretty much we take a look at the trigonometry here. So recall tan is an odd function, so that means tan of negative x is the same as negative tan of x. So here, when we have negative a half tan of negative 2x, that is basically a half tan of 2x, because the negative sign cancels out. Okay? So what we effectively have here, if I rub this out now, is a half of tan of 2x plus a half of tan of 2x, which gives me tan, not x, a, sorry, tan of 2a equals 1. 2a is equal to tan inverse of 1. If we remember from our special triangles, if we have our 45 degree triangle, we know that tan is opposite on hypotenuse, so the angle is 45 degrees. 45 degrees in radians we know is pi on 4. So we have 2a is equal to pi on 4. Therefore, a must be pi on 8. And that is the answer to this specific question. A is pi on 8. If you got a bit lost with this one here, leave some in the comments and I'll try my best to explain it, but here is all the working for it. I rubbed some stuff out here down there, but that's okay. Yeah, if you were a bit confused, try and rewind the video and see how I got it step by step. I didn't go from straight to here to tan of 2x straight away. I broke it down into parts and did some substitutions, okay? But let's move on to question 18, because this exam isn't done. We've still got 2 questions left in this paper. Okay, so consider the function p of z. 2z to the power of 4 plus az3 plus 6z squared plus az plus b, where a and b are positive integers, so that's important and we'll look at that later. One of the roots of p of z is equal to negative I. Okay, determine the values of a and b for the remaining roots. Now they have imaginary components. The remaining roots have imaginary components, so that will be important later on as well. So we know z equals negative 1 is a solution. However, we're taught in complex numbers they come in conjugate pairs. So if you have z is equal to a plus bi, the conjugate of that is going to be a minus bi. So the conjugate of this one here, z bar, will also be a solution, which will just be I. So we know 2 roots. So the first one is the one we've been given in the question, and the second one is when z is equal to I, because their conjugate pairs will be solutions to a polynomial. Right. So what we're going to do is pretty much start doing a good old long division. Long division, we'll do that a bit later, but for now let's just write this stuff up here. So this is important. So these are your roots. So you'll work out this second one pretty much just from knowing that solutions come in conjugate pairs with complex numbers. Okay, so what we're going to do straight up is a root is pretty much, if I substitute when z is equal to negative I, p, that means p of negative I must be 0. So 0, and I substitute I wherever z is in this equation. So I have 2 of negative I to the power of 4 plus a negative I to the power of 3 plus 6 negative I squared plus a negative I plus b. Okay, let's see what we can get from this. So I is the square root of negative 1. Therefore, I squared is negative 1. That's going to be important. So I to the power of 4 is I squared times I squared. So that's going to be 1. So times by negative 1. So that first bit there is going to be negative 2. Okay. I cubed is I squared times I. So that's going to be negative I. But there's a negative sign there. So it's actually going to be plus AI. Okay. I'm going to run out of room there. We know what I squared is. So I squared is negative 1 times by negative. So that's going to be plus 6. This here is going to be, rub this out real quick because I don't need it anymore. A times negative I is just going to be minus AI plus B. We can see that cancels, so we're left with 0 is equal to negative 2 plus 6 plus B. Forgive me if this B looks like a 6. Yeah, that is a B. Okay, so that means negative 4 plus B is 0. Not negative 4, positive 4. Therefore, B negative B must be negative 4. Hold up. I did this question before, I got positive 4. One of them must be wrong. Okay, that is positive, and that is negative. I got them mixed around. So that's minus 4, so the answer is plus 4. Because I to the power of 4 is now it's negative, and it's all to the power of 4. So what we have here is negative I4 is going to be negative 1 to the power of 4, I to the power of 4. That is going to be 1, and this we just worked out is going to be 1. So it's not going to be negative 2 here, it was plus 2, because negative I to the power of 4 is just going to be 1. So that's positive, and that turns into a negative as well, because what we have here is negative I all squared is equal to negative 1 squared I squared. We know that's 1 and that's negative 1, so we have a minus 6 here instead, and that's a plus. So the answer B is plus 4. Okay, so now I'm just gonna rub all this stuff out and put the B is equal to 4 in the corner, okay, because we worked out what B is. And this would be all the working for it. So now we rub this out and we use the rest of the information we have here. So now that I've worked out what B is, I can substitute it into my initial polynomial, and that will help me in this next part. Because we know one of the solutions, we worked out its conjugate pair by changing the sign of the imaginary component, which is the imaginary component is any number that has a multiple of I, where I is the square root of negative 1. So we know that z minus I is a solution because they told us, but we also know that z is equal to I is another solution because it's its respective conjugate pair. So, rubbing this stuff out, I need as much room as I can get pretty much with this next bit. Alright. So, this means z plus I is a factor of P of z, and this means z minus I is also a factor. So these are both factors. So, if I were to multiply these together, it will give me some quadratic expression, which I can then use on which I can do long division on this to break it apart pretty much. So if I were to multiply these together, I'm going to get z squared minus zi plus zi minus I squared, so z squared plus 1 is a factor of P of Z still, because I just multiply by two factors. So I can do long division. I can divide this into our polynomial, where I can replace this with 4 now, because I know what that is. So I write this as 2z4 plus az cubed plus 6z squared plus az plus 4. Rub that out, because that's a factor. So this is going to break into an expression. It'll probably be another quadratic expression, because this is z squared, and you need to multiply by another z squared to get your z to the power of 4. So now let's do long division on this, pretty much. So we pretty much go 2z4 divided by z squared is 2z squared, pretty much. So you put that up there, 2z squared, and then you multiply that bit, 2z squared, by this bit here, z squared plus 1. So you get 2z to the 4 plus 2z squared. Now, if you don't get, if this number, or whatever is here, is not the same as that, you've done something wrong, pretty much. Because now you're going to pretty much minus this entire bit here. So you have 2z to the 4 plus 2z squared. That will cancel with that. And what we have is, rewriting this down a line, we'll have az cubed, so 6z squared minus this will be plus 4z squared plus az squared plus 4. So all I did was minus this from that, and this is what I've got. And now we do long division on this bit as well. So az cubed divided by z squared is just az. So that's your next term there, plus az. Rubbing that out because I need all the stuff I can get. Then you take your az, so you go az multiply by this. So you get az cubed plus az. And you'll see this is the same as that, so you've done it right. Then you go minus az cubed plus az, cancels, and that actually cancels as well. So what we're left with for our final bit is 4z squared plus 4. Now we do that final bit, so 4z squared divided by z squared is 4. So you go plus 4 up there. Then you go, I'm running out of room, so I'm going to rub this stuff out now. So you go 4 multiplied by z squared plus 1. So we can get 4z squared plus 4. And then you rewrite that minus, so minus 4z squared plus 4. And you should get 0. Because this is a factor of p of x. So what does this mean? It means that p of, not p of x, p of z is z squared plus 1 multiplied by this quadratic expression here. So that big polynomial we got up here, this whole bit with the plus 4, is equivalent to this. All we've done is just broken up into its parts. From this first bit of information when you're told one of the roots and you can work it out, the second one because they're conjugate pairs. So what we're going to do is use our second bit of information we got told. The remaining roots of p of z have imaginary components. So this means we know what these solutions are. We know those are I and negative I. This bit here, the green bit, can only have complex solutions. So we're going to rewrite this pretty much as its quadratic form. So we'll have 2z squared plus az plus 4. Now recall a quadratic, if it takes on the quadratic formula, negative b plus or minus square root of b squared minus 4ac all on 2a, works if you have a quadratic set up like this, where This is the coefficient there and there. So this green highlighting is different with this green highlighting. So I'll change that color real quick. That's not yellow. Let's not use yellow. This represents that B. That's the only B. And then this C represents that C there. Now, if there are only complex solutions, that means this thing needs to be, this is your determinant. Oh no, not determinant, discriminant. This, your delta, needs to be less than 0 because it's under a square root. So, plugging this into its quadratic formula, the B term is your A, so you've got to have pretty much 0 is greater than your B term, which is your A squared, minus 4 times your A term, which is 2, and your C, which is your 4. So if you don't know what I just did there, all I did was recognize that's my A there. This is my B there, which I've substituted in. So you can see I've started to substitute in. And then this is my plus C, which is there. So that's how I've gotten all the way to this thing here. Okay? Because we want to work out what A is, and we're very close. So all we got to do is pretty much try and solve for A. So 0 is less than A squared minus 4 times 2. 4 squared is 16. So 16 times by 2. A plus 4. Yep. Oh, that's not C squared. Sorry, that's not C squared. So you get negative 32. So 0 is less than minus 32. Not 32, not 36, 32, sorry. It's been a long video. Move the 32 over, so we have 32 is less than A squared. That means A needs to be less than the square root of 36. Now, A was defined as integers, so that means A can be 1, 2, 3, 4, or 5, but it can't be 6 because A needs to be less than 6. So these are all the other solutions for A. So A can be these guys and B is 4. And that is the answer to this question here. There was much more working that I rubbed out here, but I just ran out of room. Okay? Let's move on to the next and final question of this video and of this exam. I can't believe we have to do this in exam conditions. This is ridiculous. These are insane. But we all want that 99.95, don't we? Okay. So, a circular base bowl has been positioned symmetrically on a Cartesian plane as shown in the diagram. The bowl has a shape generated by rotating y is equal to 4 over 8 minus x minus 1 about the y-axis for the domain. Okay, so x values belong between 4 and that value there. Okay, so starts from here, rotates there. Okay, alright, so there. The bowl is being filled with liquid at a rate of 7 pi centimeters cubed over seconds. So if you don't know centimeters cubed, seconds inverse is the same as just centimeters cubed on seconds. I assume that's seconds because it's S. If it isn't, I don't know what it is then. Determine the rate at which the depth of the bowl is increasing when the depth of the liquid reaches 1/3 of the height of the bowl. Wow, that's a mouthful, but let's break it down together. So when you hear rotating about the curve, about the y-axis, go straight to your formula sheet to your volume of revolution. So go straight to this and write, oh, that's highlighting all of it. I don't want that to do that. Go straight to this section and write this formula down. You will get a mark if you write this down. So just write volume is pi from A to B of x squared dy. Now, in the formula sheet, they have it as a function of y. A function of y means it's in terms of x, because f of x is y. So that means f of y is x, pretty much. So write it like that, and you've already got a mark if you don't know what to do, okay? Now, let's see what this is. When you're given centimeters cubed on seconds, you're actually given a dv on dt. You're given a rate at which volume is changing with respect to time. So dv on dt is 7 pi, pretty much. You're given that straight away. So all I did is I got that straight away from its units. Righto. Determine the depth is increasing when it's at 1/3. So we're looking for a d, the rate at which is increasing. We're looking for a dh dt, where the h is the height of this bowl at some particular time. Is the height of the bowl. That is a terrible way to spell bowl. Bowl at a point in time. Now, using pretty much related rates, we can rewrite this in terms of a chain rule expression. dh dt is the same as dh on dv times by dv dt, because you can see those would cancel out. So what we need to do is find, oh, that's not the correct color. We've got this term, which is this bit here. We need to find a dh dv. So we need to put this entire thing in terms of x first, because you got to work out its volume. So y is equal to 4 on 8 minus x minus 1. Put the 1 over there, so if y plus 1 is equal to 4 on x minus x, 8 minus x, sorry. You can replace this guy and this guy using algebra. You can literally swap them like, I don't know, you just can't swap them, because if I multiply both sides by 8 minus x and divide by that, you can pretty much get this expression here. 4 on y plus 1. Okay, so what you want to do now is move the 8 across. So you have, I'll write up here, minus x is equal to 4 on y plus 1 minus 8. Then you're going to divide by -1, so x is equal to minus 4 on y plus 1 plus 8. So if you've done that bit, you probably get a mark in the marking guide. Okay, we're going to chuck it into here now. And now our bounds, it's going to be, your AB is a height. So we want to put in terms of like a variable h. So h is going to be, we'll just label it h, but your a will be 0 and your b will be h. So your integral, your volume integral, will be pi from 0 to h of x squared. So this whole thing squared, because it's x dy. If you've done that, you've already made a mark. So I'll rewrite it down here so you can see it quite clearly. Volume of pi, 0 to h on -4 on y plus 1 plus 8 all squared dy. Okay. Now remember, we're looking for a dh dv. Now the h is the height at a particular point in the bowl. Okay. So technically, if I differentiate both sides with respect to y, so dv dy, I'm going to undo this integral. So I'll get pi of -4 y plus 1 plus 8 all squared. Now remember, our y is a variable, but so is our h. So what we can actually do is replace the h and the y with h. So you can rewrite this whole thing as dv dh is equal to pi on -4 on h plus 1 plus 8. Okay, we found our dv. Well, we found dv dh, but we want dh dv. So all we got to do is flip it upside down, pretty much. So you can rewrite this as dh dv, and it's 1 over all of this. So pi on negative 4 on h plus 1 plus 8. Now, we've got to keep reading the question, because we know dh dt is dh dv times by dv dt, but if we make the substitution straight away, we're not going to get a number, we're going to get a function still, and we want a number in our function. So we have 1, we can write it down here, I don't care, dh dt. So now I'm going to write dh dv, which is this bit here, 1 on pi multiplied by this whole thing here. Yep, negative 4 on h plus 1 plus 8 times by dv dt, which is 7 pi. Oh look, the pi's cancel, that's nice. So if you can see there, that will cancel with that. So I can rewrite this whole thing, dh dt is equal to 7 on all this here. Now, this hasn't given us a number, because remember, we're looking for the rate at which the depth is increasing when the depth reaches 1/3 of the height of the bowl. Now recall, what's the max height of the bowl? It's multiplied with this function here, so we want the biggest value of y, and we can work it out by using the biggest value of x. So the biggest value of y is when x is equal to 7.6, and y, remember, is 4 on 8 minus x minus 1. So all you got to do is substitute this in here, so we can get a y value, because this y value is going to be the height of the bowl. So if we times that by a third, that'll give us a third of the height. So 4 on 8 minus 7.6 minus 1. So we get y is equal to, is it 7.6? Just double checking. Yep, it is 7.6. So what we're going to get is pretty much 4 over 0.4 minus 1. 0.4 is the same as 2 on 5. So 4 on 2 on 5 is the same as 5 on 2 times by 4, which is 10. So we have y is equal to 10 minus 1 minus 1, which is 9. So the height of your bowl is 9. And you want at the point when it's 1/3 of the height of the bowl. So literally divide 9 by 3. So you want dh dt when h is equal to 3. So substitute 3 into here. So you have, I'm going to write down here, run our room. dh dt when h is 3 is equal to 7 on 8 minus 4 on 3 plus 1 all squared. And now we go work this out with our calculator now. So dh dt, well, mind you, the whole thing's without a calculator. You need to be very good with your fractions and stuff pretty quickly with stuff like this, because the rest of it's quite hard. As you can see, this is taking quite a bit. Just 4 questions alone has taken an hour for me, but I'm explaining as I'm going. The reason it would be quicker for someone taking the test is because they won't be explaining to old mate. So what you have is 7 on 8 minus 1 squared, which is going to be 7 on 7 squared, which is 49. So you get 1 on 7. dh dt is 1 on 7. And that is the correct answer for this one here. Oh, we're done, thank goodness. Righto. That was the Specialist External Exam 2020 Paper 1, Part 2 done. I did Part 1 in another video. Go check that one out where I cover the rest of these questions. But otherwise, that's it for this paper. Yeah, I'll see you in probably the next test I do.